spontaneous process. We are talking about spontaneous process and irreversible process. Irreversible process. See, what happened was, now essentially what they were trying to understand is why a chemical reaction takes place. So what is a spontaneous reaction? Let me define that and then we'll go to the next story. Because everything starts with the definition, mathematical expression and all that. So what happened was, the first is we'll look at definition of spontaneous. Because always people mistake spontaneous process with instantaneous. See, something which happens in a nanosecond is an instantaneous process. We talk about all that in chemical kinetics. A spontaneous process is a process which happens on its own. Which happens on its own. The question is, why does a reaction take place? Why is it that you keep an iron rod outside in the rainy season? In a few weeks you find that iron has rusted. Why did corrosion take place? Why did your battery give out electrons on the anode and to the cathode? Why? That was a spontaneous redox reaction. Why did it happen? So first explanation to what you call why a reaction is spontaneous is they went back to enthalpy. They put a simple condition. They said that if enthalpy is exothermic, if enthalpy change, how it is wrong, but then this is how they started. They said if enthalpy change is exothermic, then they said it is spontaneous. And obviously the vice versa was, they said if enthalpy change, they said enthalpy change is endothermic, it is non-spontaneous. That means that reaction will not happen. Now the moment they said this, this was one of the concepts which the scientists put forward. There was a huge furor and questioning about this. Why? Because two very simple things, two simple spontaneous process, proved this idea wrong. Why? Look at melting of ice. We know that melting of ice requires, so it is endothermic first of all. It is endothermic. Okay. It requires plus, so what is the Q that is required? Plus 80 calories per gram or 7.05 joule per kilojoule per mole and all that, 80 calories per gram. Okay. So it was taking, but melting of ice was spontaneous. It was happening on its own. You just keep the ice, it will melt. You don't have to do anything. On the other hand, an exothermic reaction. See, look at condensation. Now, condensation was exothermic. Condensation, what it required? It gave out minus 540 calories per gram, and that was also spontaneous. So these two examples clearly said that enthalpy change is not a criteria for explaining the spontaneity of reaction, why a reaction takes place. So what does the word entropy mean? See, entropy is given by the symbol S, And what did they say entropy is? They said entropy is the disorder of the system. Entropy is disorder of the system. They said if disorder increases. So I told, if you remember when we were talking about microscopic properties and macroscopic property, I said that what is pressure? Pressure is a macroscopic property because you can measure it with a barometer or with a manometer. Temperature, I told you, is a macroscopic property. But what was the microscopic property associated with that? The microscopic property associated with pressure was number of particles hitting against the surface of a, or against the surface of a container, which is unit area in length, unit area. So if I ask you, okay, in this 1 centimeter by centimeter, how many particles are hitting? You can't tell that. But you can say because of the hitting, what was the macroscopic property that was associated with pressure? So similarly, disorder, or some people also call it randomness, but disorder is a very better word. Random is equally better. So disorder is a microscopic property. Disorder is a microscopic property. So that the total disorder, that they said is entropy, which is a macroscopic property. So they said the disorder of a system. Now look at the case that we are talking about. So they said, so they proposed that we can measure the entropy change. So entropy change is delta S. They said we have entropy change is delta S, and delta S is nothing but what? It is entropy S of final minus S of initial. So if the disorder has increased, so increase in disorder can be measured. They said if the disorder increases, then what happens? We can, what you call, say the reaction is spontaneous. Later on we will prove that also wrong. So with this concept, people started discussing entropy. They said that entropy change, if it is positive, so that means that is greater than 0, they said reaction is spontaneous. So how did they explain the melting of ice? They said melting of ice is what? Ice is solid, so more ordered state. It is becoming a liquid, so it is what you call more disordered. So what you call, the reaction is spontaneous. Okay. Then they also proposed a law, the third law, which they said that entropy of the universe. They said that entropy of universe is always increasing. Entropy of universe is always increasing. Okay. Now how did they start the discussion? They said, look, let us talk about entropy change, because then this becomes easy. So mathematical concept of entropy is of entropy. So what is entropy? Mathematical concept of entropy is entropy delta S, the entropy change is, we can say it is Q by T. What is Q? Q is the heat absorbed or evolved. Whereas in a chemical change, we would always say that delta S is what you call, Q is heat flow of energy. So can I not say it is delta Q, the flow of energy at constant temperature? In chemical change, it will become delta H upon T. So delta S becomes equal to what you call delta Q by T. Now when it's delta Q by T, okay, then the condition here is that this reaction, this is what you call at constant temperature. So this equation delta Q by T is valid at constant temperature. When the energy change is not taking place at constant temperature, then this will be ds is equal to what you call, ds is equal to q ds is equal to q by t dq, When the amount is very small, ds is equal to dq by t. Now, how do we find out delta S? In this case, it is integration, final minus initial and all that. So, in that case, your entropy change at just entropy change, constant temperature and not at constant temperature, will be delta S will be equal to integral dq by t. We are going to use this somewhere later on. It is clear? So understand this. So mostly what we are going to talk about today is this situation at constant temperature. Okay. Now what happens is entropy change at variable temperature. Let us put that now. Entropy change at variable temperature. Then this becomes delta S becomes equal to dq by t. Now what happened was, let us take some examples to understand. So what they said was, why is something spontaneous? Because entropy change is spontaneous. Now this led to a problem. Let us go back to our example with which we started. See, look at what you call ice. So melting of ice. Melting of ice. So in melting of ice, what happens? 80 calories per gram was absorbed by the system. 80 calories was absorbed. So delta S will be equal to delta Q, and at constant temperature, 0 degrees centigrade. So this was whatever was the value, delta S was positive. It was absorbed. But condensation was a spontaneous process. Condensation was a spontaneous, or is, there is no was. English is wrong. Condensation is a spontaneous process. Condensation is a spontaneous process. When we talk of condensation is a spontaneous process, in condensation what happens? What is the delta Q? It is minus 540 calories per gram is the heat release at constant temperature. So here if you technically look, delta S will be negative. If delta S is negative, that means less than 0. We expect it to be non-spontaneous. So the scientists realized that something is wrong. So what happened was, they realized that every time we are focusing our attention only on the system and not on the disorder of the surrounding. Not on the disorder of the surrounding. I'll give you a simple example. It is clear. Suppose we have an air conditioner. Suppose we have an air conditioner at home. Is this clear? Why to suppose? We have an air conditioner. Okay. What happens is, the air conditioner is withdrawing the heat from the room. Okay. So from the aspect of the room, if room is the system, then what is happening? It's withdrawing the heat, okay, and throwing it out. So from the room as a system, what is happening? The energy is what? It is exothermic. But what is happening is, this energy is going out, and from the perspective of the surrounding, that is the air around, what is happening? That is receiving the energy. That is receiving the energy. Is this clear? And so for it, it will be an endothermic process. So they realize that in isolated conditions, we cannot talk of only the system. We have to talk about a system and surrounding, but these conditions are non-isolated. That means there is exchange of energy between system and surrounding. So there is going to be a change in the disorder of both the system as well as the surrounding. So what did they say? Therefore, the delta S of the universe, so they put it this point, delta S of the universe is the sum total of the delta S of the system plus delta S, which is the surrounding. So what did they say? Now by using this, they explained the condensation. See, they said when there is condensation, no doubt. So what is happening? Steam getting converted into Steam getting converted into water, that is liquid. Yes. Delta S, the entropy of the system. Try to understand. Entropy of the system. Now, steam is gas or disorder is very large. Disorder is very large. So, what is happening is when it becomes liquid, your delta S is less than 0. But what is happening is it is exothermic. It is exothermic. Is this point clear? It is throwing out heat into the surrounding. It is throwing out heat into the surrounding. When it's throwing out heat in the surrounding, the delta S, this is of the system. Delta S of the surrounding, for the surrounding it is getting heat, disorder is going to increase. So delta S is going to be greater than 0. So where they said, why is it, what do you call, why is it spontaneous? They said the delta S total happens to be greater than 0. So for spontaneous, they said why? Because this, the entropy change, the disorder of the surrounding is so much larger that positive value is much greater than the negativity of the disorder due to the disorder which is decreasing in the system. So net total disorder of the universe is increasing. So this change in the system is becoming spontaneous. This change in the system is becoming spontaneous. Is this clear? Now we have entropy change. Entropy change in isolated system. This is a question which they ask in any entrance exam. What is entropy change? Because we said, is the system greater than 0 or is it the system plus surrounding greater than 0? What is it? Is this clear? So in an isolated system, the best example we can take is diffusion of gas. Diffusion of gas. This seems to be a very common example in all textbooks. So even I have picked up that. Is this clear? So what happens is, I have two gases in these two chambers. Two different gas. Is this clear? For example, I can have N2O5 or NO2, brown in color. I can have NO2 and I can have oxygen. What do you call it? Block these two gases with the help of a valve. Is this clear? Now, moment I lift the valve, and this is surrounded by a diathermic boundary. So, diathermic boundary means there is no way any heat is going from the system to the surrounding or surrounding to the system. So, this is isolated. Is clear? Cover it with thermocol or something like that. But what do I realize? That moment I release the valve or open up the valve, I can see both the arms have become brown because of nitrogen dioxide moving from here and obviously oxygen moving from here. So there has been a diffusion. So diffusion is spontaneous. So what? Now there was no question of taking energy from the surrounding or from the system. So in this case what happens is, so delta S definitely was greater than 0 because you are seeing it. You are observing that this diffusion is what do you call happening. Diffusion, physical change is what do you call spontaneous. So but now we had this delta S of the universe is equal to delta S of the system plus delta S of the surrounding. So there cannot be a change. There was no change of energy between system and surrounding. So this is the question that we have to remember. That in case of an isolated system, the entropy change is only because of the change in entropy of the system. So diffusion itself is increase in disorder. Diffusion of the molecules within the system is what do you call an increase in disorder, and so therefore it is spontaneous. That is the logic. So entropy change in a non-isolated system. In a non-isolated system, what happens is you have nothing but delta S will be equal to what? Delta S universe or total. We can even say it is total is equal to delta S of system plus delta S of surrounding. Delta S of surrounding. This is clear. Now what happened was, here the problem was sometimes the delta S of the surrounding becomes very difficult to measure. I just gave you an example. The air conditioner is withdrawing heat from the, what do you call, room, from the room and throwing it outside. So whatever is the temperature drop, okay, whatever is the temperature drop, that we can always measure. We can measure how much was the MC theta or NCP delta T will tell you the heat change at that temperature. But when it goes into the surrounding becomes very, very, what do you call, large. The surrounding is very large. So exact measurement of the entropy change in the surrounding cannot be found out because it hardly makes any difference. One air conditioner, if it is on in Bombay, it will make a difference to the temperature in the room. 25 to 19, it has come down. It has made a difference to us. It has made a difference to us. But that much heat being thrown out, will it increase the Bombay ka temperature from 25 to 35? No, the disorder is going to be, what do you call, dispersed over so much large volume that it is minuscule. So calculating here, see, disorder in the room was easy to calculate because the temperature dropped 25 to 19, 25 to 20, rakho na easy, 10 degrees centigrade, NCP delta T, number of moles of gas, Cp the specific heat into delta T upon at that temperature whatever it is. It was not a constant temperature, na? So at that temperature whatever you are measuring, is this clear? That could be calculated. So entropy change in the system could be calculated. But that same amount of energy outside, thrown outside. So what was exothermic here? What is being pulled out? It will be exothermic for the other one. So same way, if your heat is supplied for the system, suppose we are drawing heat from the surrounding to the system. Sorry. For the system it is endothermic. So your delta Q upon T will be positive, see. So consider a system, okay. Consider a system, let us consider like this. So you have supplied delta Q amount of heat. So from the point of view of the system, okay, this was endothermic. You could find out the delta Q change. How much was it? If it was a gas, NCP delta T or NCP theta. This surrounding, the surrounding gave that much energy. So this was endothermic. From the surrounding point of view, NCP theta, whatever is the value, that was exothermic, that is minus. It is releasing the energy into the system. For the system, it is endothermic. So this we can calculate. This is your delta H of the system. So what they said was, look, delta S total, let's now say only it's delta S, is equal to delta S of the system minus, because from the surrounding point of view, this is surrounding, which is too huge. Did the disorder affect it? Suppose 80 calories was absorbed by the ice from the surrounding. What difference did it make to the surrounding air? It made a difference to ice. Physical change took place, spontaneity happened. But did it make the whole room cool? Nothing. It's not possible. Otherwise, we would not buy air conditioner only, na? It is clear. So what happens in this case is the surrounding is too large. So that became from the same value. This is minus delta H upon T. Minus delta H upon T. So what they did was multiply throughout by T first. So T delta S is the entropy change of the surrounding, okay, is equal to delta S of the system. We multiply T delta S. T delta S minus delta H. Okay, so this is system. I'll still keep it. Okay. So putting a minus sign throughout, what do we get? Minus T delta S is equal to delta H minus T delta S of the system. Okay. Now understand this. So this, what is this minus T delta S? This was called as free energy change, delta G. So what is free energy? Let us understand that. This is clear. For that, I'll still come back to the same, kettle experiment, because there we had missed out some point, you never realized, nobody asked me that. See, what is happening is, there is a, see, now understand why did the work happen? Okay, why was it spontaneous? Why did the reaction become spontaneous? See, what happens is, see, you remember what we did was, whatever was the temperature, we brought it to 100 degrees, 373 Kelvin. So at 373 Kelvin, whatever heat we supplied, first what happened? First it went in converting the water into steam. It did not directly start doing the work. Then, so that amount of energy Q, which you supplied at 373 Kelvin, did what? Just caused a phase transfer from water to steam. From water to steam. So this is the free energy change. Whatever energy you supply, okay, so then some amount of more Q plus something W you supplied, that went into, so something else, Q plus a Q1, another Q1 you supplied, then that was used for moving the, moving the lid up and down. So initially, so whatever is the total energy you supplied was Q1 and Q2. The total energy, water at 100 degrees if we start, first we supplied energy which only caused a change in phase. That did not do work. Beyond that, when you supplied another extra energy Q2, then what happened? So total energy supplied was how much? Q1 plus Q2. Out of Q1 plus Q2, only Q2 amount went into what? Went into doing mechanical work. What about Q? What about Q1? Q1 is the energy, which is the free energy change. Is this clear? So whenever the free energy change is negative, so whenever the free energy change is large, it is negative, because minus T delta S, na? So then what happens? The reaction becomes spontaneous. Is this clear? So what happened? They said, so when delta G is negative, so therefore the equation became delta G is equal to delta H minus T delta S of the system. This is called as Gibbs equation. So what is this Gibbs equation trying to tell you? It says that when you supply energy, some amount of the energy is used for doing work and some amount of the energy is used for only doing change in internal energy. Okay, change in internal energy. So work, see, that means you took 100 joules, 80 went into increasing the temperature, correct? 80 went into increasing the temperature, 20 joules went into mechanical work. So that is now not considered as energy, it has become work. That is the free energy change. So whatever energy was used from the energy supplied to cause work to be done, that energy is lost because energy got converted into mechanical work. That is called as free energy change. So that value will be, if it is negative and more negative, is this clear? Then what happens? The reaction will be spontaneous. So delta G should be negative. The change in free energy. Is this clear? The larger the change in free energy, what happens? The reaction will be what you call spontaneous. So delta G is the amount of energy from the energy supplied which got converted into doing useful mechanical work. So therefore that energy, so you had, suppose you had 100 calories, you had 100 calories, because calorie is unit of heat, yaad rakhna, and joule is energy of unit of mechanical work. Okay, so 100 calories you supplied, okay, 80 calories was used for A, and work equal to 20 calories in joule was done. Work equal to 20 calories in joule was done. Is this point clear? So that energy is lost, right? That is no longer heat energy. That is now mechanical work. So that value, because initially when you supplied heat, did you have mechanical work? No, zero. Then a work was done. So this difference represents that energy which has been used to convert into useful mechanical work. That in thermodynamics we are calling as free energy change. So this is the Gibbs equation. Delta G is equal to delta H minus T delta S. At standard temperature, that is 25 degrees centigrade, standard enthalpy change delta G0 is equal to delta H0 minus T delta S. Now you should know it is this time. Is this point clear? Conditions for spontaneity. See, conditions of spontaneity is what? When delta G is greater than 0, it is non-spontaneous. When delta G is less than 0, it is spontaneous. Means the reaction, the physical change or chemical change will take place. When delta G is equal to 0, we say the situation is, it is in equilibrium. It is in equilibrium. Is this clear? Why? Because see, suppose from A to B, if it is reversible and equilibrium, what happens? The amount of disorder increasing, the same amount of disorder is also caused over here. So net, your T delta S will be 0, and so what will happen is that T delta S of the surrounding will be 0. So your delta G will also be equal to 0. So at equilibrium, delta G is equal to 0. Now what are the conditions? There is a table which we had to teach you. Very, very important. I don't want to make a mistake in that. We'll refer the book. Okay. Now look at this condition. We have delta H, delta S, and we have delta G. Okay. Basic equation that we are using is delta G is equal to delta H minus T delta S. So let us look at the conditions. The first condition is a very, one or the other combination of this is a part of one MCQ in the entrance exam. The first is, let us say delta H is exothermic. So delta S, that means there is an increase in what you call entropy change. There's an increase in, so delta H is exothermic. That means this is positive. Sorry, this is positive. Exothermic means this is negative. Sorry. Delta H is exothermic means delta G, this thing is negative. Delta H is negative. Your delta S is positive. So positive into negative is negative. So here what happens? Your delta G is what you call less than 0. It is negative. So reaction will be spontaneous. So conclusion kya hai? It is spontaneous at all temperatures. Spontaneous at all temperature. Let us look at the next condition. Next condition is again, this is exothermic, but delta S is negative. This is clear. So your delta G can be negative or positive. What is it that I am trying to tell you? Listen carefully. So what am I trying to tell you? Look, if delta H is negative, but your temperature, see, look at what we are saying. Delta S is, in the second case, delta S is negative. So negative into negative is positive. Second case, your delta S is also negative. So negative into negative, this whole thing is what? It is positive. So delta H negative, T delta S is positive. So when will it be spontaneous? It will be spontaneous when T delta S is less. This factor, when this will T delta S be less, that overall it is negative, low temperature, when T is very less. So this is spontaneous at high temperature. So, no, sorry, I'm thinking of the next one, and spontaneous at, I'm thinking of the next alternative. So spontaneous at low temperature, and at high temperature it will be non-spontaneous. Look at the third case. The third case is, this is endothermic. Your delta H is positive. Your delta S is positive. Again, this can be positive or negative. It can be spontaneous or non-spontaneous. Why? Again, I have to explain. When it will be spontaneous and when it will be non-spontaneous. Look at this case. So the equation was delta G is equal to delta H minus T delta S. So your delta H is positive and your delta S is positive. Barabar? So this is positive. So for the whole thing to be negative, this minus T delta S has to become negative. When will that become negative? When temperature becomes high. So this will be spontaneous only at high temperature. So I was thinking about the next one, then I made the mistake last time. I am mentally preparing for the next one. Now fourth, this is endothermic and this is negative. So this is positive and this is negative. So negative into negative, positive. Whatever situation it will be, always delta G will be greater than 0. So in this case, what happens? It will always be delta G greater than 0. So it is non-spontaneous. Such a reaction is non-spontaneous at all temperature. It is non-spontaneous at all temperature. Is this point clear? So now, how do we connect this to what we call delta G? Free energy change. Free energy change and equilibrium. So we know that delta G is equal to delta H minus T delta S. Okay. So at equilibrium, what is going to happen? Delta G, stand free is going to be 0. So delta H becomes equal to T delta S. So your T, what happens is delta H upon delta S. So what happens is, there is a cutoff temperature. The cutoff, below the cutoff temperature, the reaction is non-spontaneous, and above the cutoff temperature, the reaction will be spontaneous. You will say, sir, what is this you are saying? I will give you an example. See, we know that C plus carbon solid, that is coal I am talking, C plus O2 oxygen gas forms CO2 gas. See, this delta H is around minus 285 kilojoule per mole. It's 285 kilojoule per mole. If I go by the first logic, that if the enthalpy change is exothermic, it should be spontaneous. All the coal present in coal mine, moment it comes in contact with air, it should burn, just like a phosphorus. Now, phosphorus, moment you bring in contact with air, it burns. But does coal burn like that? No. You keep coal at room temperature for 100 years, nothing is going to happen to it. But the same coal, have you seen how they start the tandoor? You may not have seen, observe properly, because your generation is too much fixated on the gas and all that. A tandoor has to be actually started, What they do is they put the tandoor, all the coal in the tandoor, and then they put little kerosene. Now, kerosene catches fire instantly. Moment you bring the matchstick at room temperature, combustion of kerosene is a spontaneous, it burns. Now, when kerosene burns, what is it going to do? It's going to release heat. Who is going to absorb the heat? The coal, which is absorb the kerosene, coal absorbs the heat. And slowly what happens? The temperature of the coal goes to around 700 degrees. Now at 700 what happens? This reaction becomes delta G less than 0, spontaneous, and coal starts burning. So to initiate the burning of coal, you have to use something to cause heat, to raise the temperature. So at that temperature, what happens? This reaction. So this reaction is not normal. This will not happen at room temperature. This will happen at a temperature beyond say 700. I mean, I'm giving an example. Don't take it in mind, it's absolutely 700. We can calculate that temperature. What is the temperature? Delta H at that temperature, this is at room temperature. Delta H at that temperature, Kirchhoff's law you will find out. And then delta S, divide that, you will get the temperature at which coal will start burning on its own. Coal will start burning on its own. Is this clear? So this is the connection of free energy change and equilibrium. Is this clear? So below the equilibrium, what will happen? Below the equilibrium temperature, it will be non-spontaneous. Above the equilibrium temperature, what will happen? It will be spontaneous. So it's not that all reactions, once you say it is non-spontaneous, the story is over. It will depend on the temperature. It will depend on the temperature. Is this point clear? Now, if we have free energy change, and equilibrium constant. See, what happens is delta G will be equal to standard enthalpy change plus RT ln Q. What is Q? Q is reaction quotient. Q is reaction quotient. So whenever we have a reversible reaction, not at equilibrium, then ratio of concentration of product upon the concentration of reactant is reaction quotient. But at equilibrium, what did you say? You said that delta G, the free energy change, is equal to 0. Is this point clear? So if this is 0, what do we get? Standard free energy change plus RT ln. Now your Q will become, therefore, Q will become equal to K, equilibrium constant. So now you take it over here, what do we have? Standard free energy change is minus 2.303 RT log to the base 10 of K, the equilibrium constant. We'll require this. This is the reason why I taught what we call thermodynamics first, because this is going to be used in electrochemistry. Is this clear? So this is the connection between equilibrium constant and, now what is third law of thermodynamics? I write the statement and explain what it is. See, if you remember, I told you absolute enthalpy cannot be found out. Because moment you try to find the absolute enthalpy, you are discussing the rotational energy and all that from the internal energy component. So therefore we said at standard temperature element is 0. We assumed it is 0 and then proceeded. This is clear. But that's not the case with entropy. That's where third law comes in. Third law says, defines when is entropy 0. What does third law do? It defines when is entropy. It states that, what it states that entropy of perfectly crystalline substance entropy of a perfectly crystalline substance, okay, is 0. So you are defining when is the entropy 0. Perfectly crystalline 0 is 0 at absolute 0 temperature, at 0 Kelvin, that is absolute 0 temperature. Now, there is one more point I have to tell, which is asked. But you realize that there is some entropy. If at absolute 0, that is 0 Kelvin, there is some entropy, then that is called, if any entropy is present, if any entropy is present, it is because of impurity. It is because of impurities. And remember this word, this is what is asked in entrance exam. It is called, and it is called residual impurity. It is called residual impurity. Is this point clear? See, there is one